get through. As usual, we won't get through everything, but since 2 or 3 are somewhat conceptual, I do want to ask for help from student helpers who will help translate, and the TA who will help vet the solutions. So let's see, where is the where did that go? Okay, so the lesson plan is, let's try to get through at least questions 12, 13, and 14, and in this order. So I'd like to begin by asking Honthik to come help present question 12. Okay, very good. So, so question 12, if you remember, is about showing Gauss's divergence theorem, but now in polar coordinates. So the question says, so there's a region T. So this is like some volume. This is some volume which has a surface which is represented by S. So for example, think like, just as an example, think like the volume T is like a ball, and the surface S is like the surface area of the ball, right? And the volume. So now the question is to prove that the volume is 1/3 of the double integral over the surface of r cosine A dA. So this is a surface integral where r is the distance of the point. So this is r in polar coordinates. It's the distance of the point from the origin, right? Now, when you look at this formula, you should be reminded of what you saw in the in Green's theorem. In Green's theorem, you saw that the area of a region is given by a single integral of a certain function along the boundary, right? So this is like a higher dimensional version of that. Instead of the area being given by a single integral, like the area is actually a double integral, but you can reduce it to a single integral just along the boundary. Similarly, here the volume should be a triple integral, but you can reduce it to a double integral along the surface, right? So that's the intuition between this thing, and this shows the connection between Gauss's divergence theorem and the Green's theorem that you've already studied, and in some sense Stokes' theorem is also just a version of that, right? These are all related to each other. By the way, you're listening and you'll help translate these conceptual points, right? Okay, fine. So now we're going to look at the solution that was given by Honthik. The hint given here was to use a particular vector function. F is x, y, z, and then use the divergence theorem. I should have been specific here. So phi here is the angle given by the directed line OP and the outer normal S at P. And here, okay, so we're doing question number 12. Okay, good. So in this case, as is often the case, we have also a separate nice solution by Vejia. He'll have a chance to present later, but there's a nice picture over here if it helps you think about this. So there's some surface which is the S, which encloses the region T, right? And then the normal vector over here is given by this n vector. Phi is the angle between the normal vector and the line segment joining the normal vector to this point, right? So that's a point phi over here. Okay, so William has a solution. So does Honthik. Let's look at Honthik's solution. I'm going to try to highlight, from my perspective, the major points of the first part of the solution. And what he does is, so the volume is just the triple integral of the constant function, like 1, just triple integral of 1 times dv, right? That's the formula for the volume. Just like the area is the double integral of 1 times dA, right? So that's what you have over here. Now, the divergence of the function x, y, z is actually 3, right? Because the divergence is del x by del x plus del y by del y plus del z by del z for this particular function, right? So therefore you have to divide by 3 to keep this 1, to make this 1, right? Now this raises the question, why did we choose the vector function x, y, z? Why didn't we choose just the vector function, xi? Why not just that? And that could have worked, right? we could have gotten a formula just with the x component as well. So at least up to this step, we could have just done 1 times the divergence of xi plus 0j plus 0k. So we could still have done that step. But then the later steps would have been trickier to use, right? So over here, just to get a nice formula, we carefully chose this function xi plus yj plus zk that makes the future proof a little bit easier, right? Okay, so we did that. So this is just the divergence of this function f. Now the divergence of this function f is the so f dot dv. So now we use the divergence theorem. So that's nothing but 1/3 times the function f, the vector function f dot the surface normal vector times dA. The surface normal vector. Now here we can use the figure that is nicely provided to us over here. The surface normal vector dot dn is just going to be given by the magnitude of this times the magnitude of this times the cosine of the angle between them, right? And since this is a normal vector, the magnitude here is 1, so it's just the cosine of this angle. And now because we chose this vector function f to be in a nice form like x, y, z, so now in polar coordinates we can write it easily as the square root of x squared plus y squared plus z squared, right? So that times the cosine of the angle between the vector function between the function xi plus yj plus zk, which is given by excuse me, which is given by the coordinate position of this point. So xi plus yj plus zk is given by the line segment, is given by the vector joining the origin to this point over here, right? Times the normal vector, which is always pointing perpendicular to that. Okay, and now we can just substitute. This quantity here is just r, so now we have r cosine phi dA, right? So that's this proof over here. Okay, so the summarizing points I'd like you to, like the points that I do want you to remember to highlight in a summary are the following. So firstly, in the question itself, when you're discussing the question itself, you should first of all remind people your T is a volume, S is a surface, right? So T is 3-dimensional, S is 2-dimensional. Secondly, the relationship between this formula and a similar formula for Green's theorem, where we had the area is given by a single integral, right? That was the second thing. The third thing, well, the hint given here is that you can use the divergence theorem with this particular vector function. So that's when discussing the question, these 3 points. In discussing the solution, so firstly, the volume is just the triple integral of the constant function, right? It's a simple point, but worth highlighting for your classmates. The fact that the divergence here gives you a factor 3, so you divide by 3, that's the second point. The third point is you could have used other functions, but then that would have made the proof more complicated later. And then use the divergence theorem, make sure people see the figure here, right? And the fact that xi plus yj plus zk is the vector joining the origin to this point, and the surface normal vector is here, so you have angle phi between them, right? So collaboratively, you and Vijaya have a nice little solution, and then the rest is just calculation, right? Okay, so Mantik is going to help us with this, and let's begin.
刚才教授就说呢，就要留意这个 T 是一个体积，不好意思，我普通话不是太好。还有 S 是一个平面，所以他就想我们把这个 Gauss's divergence theorem 还有 Green's theorem 就做一个对比，就他们很相似，就是Green's theorem 就是把 2D 的和1D 就是double integral 会用一个single 一个 integral 来可以计算出，这个 Gauss theorem 呢就是把这个 triple integral 就用这个 double integral 来解出，所以就两个都是很相似的。
Okay, and let's go to the solution. Okay.
然后 solution 这边教授就说这个volume 呢其实就是这个 dv 的 triple integral，还有这个 divergence of 那个这个 x y z 呢就是3，所以前面我们要除以3， 还有他说其实可以选其他的f 不一定是 xyz， 只是这样会计算的比较简单。还有就是这个f 到 n 的时候呢，这个 cosine phi 呢就是因为 f 是 xyz， 所以这个f 到 n 呢就是其实就可以看这幅图啊，就是那个 phi 就是这个 origin 到那一点的 factor， 还有这个 surface normal factor 中间的角，所以就是 cosine phi， 然后剩下的就是简单的计算，就这样。
Okay. Okay. Oh, he gives you a full point over here. Very good. And then I won't spend too much time on this, but let's also just look at the second part of this question. So the second part said, well, okay, now that you have this formula, how can you do it? How can you use it to do some calculations? So, for example, find the volume of a ball of a sphere of radius a using the thing that you've derived earlier. So over here, Honthek then said, okay, so here he chose to use, instead of spherical coordinates, he chose to use cylindrical coordinates, right? So r cosine v, r sine v, and then the height is given by u over square root of, so u is the height, it's the z coordinate. So u over square root of a square minus u square, and then he derived the ru, rv, found the normal vector, found the integral, and then wrote the volume as so he was able to compute that it's 1 over 3 r cosine phi, where r is given by a cosine phi by 1, and then you can then just use the formulas that he's already derived to show that the volume is given by just 2 pi a times the integral of u over square root of a square minus u squared du. So that gives you by the formula for the arc tangent. What is this? I've forgotten. Do you remember what the integral of a over square root of a square minus u square is?
Definite integral is
a. 2 pi a square, but the indefinite integral is arc sine, arc. Okay.
Square root of a square minus u square.
Oh, right. Oh, okay. I'm sorry. So clearly I need to review my basic calculus as well. But the indefinite integral of this is square root of a square minus u square. And then when you substitute in the limits 0 to a, then you get 2 pi a cubed by 3. Okay, that's what maxima is for. So anyway. Okay, good. So yeah, this is mostly calculations, but Honthek will describe it.
这个呢，我就选了，就不是用 spherical coordinate，就用了另一个叫做说是cylindrical coordinate，就跟它video 还有 PPT 里面的一样，就找出那个 RU 和 RV， 然后计算那个 normal factor， 然后R 就是 A， 这个很明显，然后 cosine phi 是1的话，是因为那个我们的在一个球体那个 surface normal factor， 还有你origin point 到那一点的 factor 两只的中间的角一定是0，所以 cosine phi 是一定是1，所以。
You're doing a better job than me. I forgot to mention why so let me, because not everyone understands Chinese, let me repeat in English what Honthek just said, which is an important point. Why is cosine phi always 1? Because the object here is a ball, right? It's a sphere. So the surface normal vector, let's look at the image here. The surface normal vector will always be pointing in the same direction as the radial vector, as the vector joining the origin to that point over there, right? So therefore they will be in the same direction. Therefore phi will be 0 and cosine phi will be 1. Okay. Yeah. Thank you for doing a better job than me. So pointing out why cosine phi is always 1. So continue, please.
然后把cosine phi 和 r 就带进去，就也把 n 就是 的数值带进去，然后找出那个 integral， 我们就可以计算出这个一半的球体的一半的体积是 2 pi a cube over 3， 然后乘以2就是整个球体的体积。
Okay, very good. I think that was a very good solution. Okay, good job. No fruits today. I'm sorry. Tomorrow I'll remember to. Okay, good. So yeah, and of course a bonus point to the presenter, as has already been mentioned here. Okay, question number 13. So I'd requested help from Zishuan and Vejia. So there were no solutions posted for part B. I'll discuss that myself. But first, can Zishuan, if he's here, come? Okay, there we go. Franklin is going to discuss part A. So while he's coming here, let's begin by looking at what this is saying. So again, question number 13 is, I mean, there's some calculation, but it's also conceptually quite important. Okay, so let's understand conceptually what this question is asking us to do. The first part is actually just calculation, but it gets us starting to think about the problem over here. But what is the problem really? So it's saying, suppose someone gives you two functions f and g that are harmonic. So remember what harmonic means. It means the Laplacian of these functions is 0. It means nabla square f is 0, nabla square g is 0 everywhere on that domain, right? That's what harmonic means. So this is the domain D. This is some volume D. In particular, it has a region T. So this is a volume T, and the surface is S. And you know, everything is satisfied. All the conditions are satisfied. The functions are continuous, and all the other things that we want for the divergence theorem. All of those are satisfied. Okay. So the first part, which is what Franklin here solved, basically asks you to do a calculation and show that if these functions are harmonic, then f times what is this called? The normal, the partial derivative with respect to the normal vector of g minus g times the partial derivative with respect to the normal vector of f, that times dA is equal to 0. So this is mostly calculation, but this calculation will be useful for the next part. Okay. Which there isn't a posted solution for, but we'll look at that. So what did Franklin do? So this is the function to be evaluated. Now, by the definition of del g by del n and del f by del n, this is nothing but the gradient of g dot n. That's what del g by del n is. Similarly, del f by del n is by definition just the gradient of f dot n, right? So you just substituted in the definitions here. Then he used the divergence theorem. So here now you have, so here you have a vector function. Remember, so gradient of g is a vector function, gradient of f is a vector function. So you have a vector function here dot n. So this quantity here, by the divergence theorem, it's going to be the divergence of this quantity dv. Now when you, so now he does some calculations here, and he basically notices that the divergence of f times the gradient of g minus g times the gradient of f is equal to f times the divergence of g minus g times the divergence of f. Okay. So and because we know that f and g are harmonic, because we know that they are harmonic, therefore both of these Laplacians, both of these like nabla square g, nabla square f are 0. And therefore this quantity here is going to be 0, right? So therefore we can just substitute in the fact that the divergence of f times the gradient of g minus the g times whatever. So this quantity over here is 0. So you're just integrating 0 times dv over this region, and therefore you get 0, right? So those are the calculations. Okay. So now the points I want you to repeat, Franklin, are the following. So over here, you have some region which is nicely behaved, some functions which are nicely behaved. In particular, they are harmonic, so the Laplacian is 0. Nabla square f is 0, nabla square g is 0. And here, this is just a calculation to show that f times del g by del n minus g times del f by del n dA is 0. And then your solution basically did a few steps. The first step was to substitute in the definition of what del g by del n and del f by del n are. So that's just the gradient of the corresponding function dot the normal vector. Next, you use the divergence theorem, right? Finally, you evaluated the divergence of this and showed that it's basically related to the Laplacians of these functions. Then you use the fact that the Laplacians must be 0 because they're harmonic, and then you're integrating 0 times 0 times dA, and therefore you get 0, right? So those are the steps, and let's hand it over.
好的，这题是要证明这个式子等于零。首先，在我这个答案里面，第一步我把del g 除以del n 这个根据它的定义，把它转换为了是等于 gradient g 点成n 向量和 delta f 点成 n 向量的这个形式，就把它化解成这个形式。然后呢，再根据 divergence theorem 把这个式子转化成右边这个式子，把它转化成divergence f gradient g 减掉 g gradient f 的这个形式。然后现在我们来计算这个 divergence f 的gradient g 减 g gradient f， 然后我们会得到的结果就是这个 divergence 这个会等于 f 乘以Laplacian g 减掉 g 乘以 Laplacian f， 然后根据这个题目里面的定义 f 和 g 都是 harmonic 的， harmonic 就说明这个 f 和 g 的 Laplacian 都等于零，然后我们就可以得到这两个东西等于零，也就是说这个式子里面这个 divergence 这一块就等于零，它就是对零做一个积分，最后的结果也就等于零。
Okay, very good. We also get the sign from the TA, so good job. All right, now nobody posted a solution to the second part, so let me just do the second part myself, and conceptually it's quite important. So the second part is now saying, suppose the del f by del n and del g by del n, so del f by del n and del g by del n are the partial derivatives of the function with respect to the normal vectors. So suppose these are equal, just on the boundary, then the functions must be equal everywhere in the whole region. Okay, let's understand what that's saying. This is actually quite important. This is related to what in physics is called a so-called holographic theorem. Okay, so it's basically saying someone's given you some region T over here, and now someone has told you what the function is behaving like. So what the potential of some potential function is behaving like on the surface. Someone's told you what del f by del n is like over here. Okay, so the claim is, if someone has told you the value of del f by del n everywhere on the surface, then in fact f is essentially uniquely defined, and f is harmonic, then essentially f is unique up to an additive constant, everywhere in T, additive constant C everywhere in T. So let's understand what that means, everywhere in T. So basically what that's saying is, suppose there were two different functions f and g, both of which were harmonic. Okay, so suppose f and g are both harmonic everywhere in this region, that is nabla square f is 0 here, nabla square g is 0 here, and the only other thing we know about f and g is that their partial derivative, like del f by del n on the surface, just on the surface, is equal. Then in fact f must be equal to g plus some constant. That constant we can't figure out, but f must be equal to g. Okay, now that's quite important, right? Because from physics, like if you think about it, like these f and g are like potential functions, right? So, and the del f by del n is something like the electric field. So what this is telling you is, if someone tells you what the electric field on the surface of an object is, only on the surface, then you uniquely know what the potential is everywhere inside the object, not just on the surface, but everywhere inside the object up to an additive constant. Okay, and remember that additive constant is important, right? Because potential functions, like the zero of a potential function, is arbitrary, right? Like you can define the 0 point to be anywhere, but then everything else is relative to that potential function, right? So that's the physical meaning of this question. The physical meaning of this question is, once someone has specified, or at least a physical example for this question is saying, once someone has specified the electric field everywhere on the surface of a volume, then the potential function is uniquely defined within that volume. Okay, that's a useful way of remembering this. Okay, so how do we prove this nice little theorem? So using very similar calculations to what Franklin did in the previous part. So I claim if you look at the double integral of, so now let's just for a second, instead of f and g, let's just think of some function u, and let's look at u del u by del n d ds. Okay, so let's consider this. And then by the divergence theorem and by similar calculations to what Franklin did earlier, you should be able to show that this is equal to the triple integral of the gradient of u absolute value whole square d integrated over the volume. Okay, so it's a similar calculation. You can just use the divergence theorem and do the same calculation as before, and you'll get this formula over here. Okay. Now, suppose someone has given us two functions, f and g, both are harmonic. Then in that case, we know that nabla square f is equal to 0 and nabla square g is equal to 0. Okay. So therefore, f minus g is also harmonic, right? Because the nabla square operator is linear. So nabla square f minus g is also going to be equal to 0. And now let's just set u is equal to f minus g. Let's define u to be f minus g. Okay. So in that case, what are we evaluating? So nabla square u is going to be 0 because of these two things here. We'll have nabla square u is, sorry, I made a mistake. This should be nabla square u. So nabla square u is going to be equal to 0. And since nabla square u is going to be equal to 0, so you're going to be integrating 0 times dv in this whole volume. And since 0 dv is equal to 0, so that tells us that that basically you have that this integral is going to be equal to 0, and therefore you have that f is equal to so the only way that this is going to be equal to 0. Oh wait, I'm making a mistake here. So u okay, you know what? I'm making a mistake here somewhere, and I don't want to cause problems to the class. Let me come back to this after I think about it. Okay. Of course, if someone else solves it before me, that's great. Bonus points to you guys. But part B, I have to come back and just think about it. It's related to the divergence theorem and the calculation in the previous part. These are some of the steps, but I'm missing just one or two key ideas. Okay, we'll come back to it. Let's move on to part number C, for which who did I request help from? Oh, right. So Vejia. So can William come and help us? So part C, remember, is asking us to show that the Laplacian can be represented independently of coordinate systems in this form. So the Laplacian is nabla square f is the limit of something here, we'll understand it later, times 1 over the volume of t d. Okay, so let's draw a figure here so we can see what's going on. Okay, so let's take some region t. Let's take some region t over here. Now dt is going to be, let's see how dt is defined. So dt in the question is defined as the maximum distance of the points in the region T bounded by St from the point at which the Laplacian is evaluated. So basically what's happening is we are taking a very small volume, we keep shrinking the volume of T over here, we keep making T smaller and smaller. So all of these points over here keep getting closer and closer to each other, okay? So dt, you can think of dt as being somehow the radius of the ball which encloses the volume T that you're interested in, okay? So as the dt, as the radius of that enclosing ball gets smaller and smaller, you want the you want to evaluate some integral. So now we're going to take the limit of this radius of the ball going to 0 times 1 over the volume of this small region T. So this volume is also going to go to 0, but then the integral that you're evaluating, del f by del n dA, that is also going to go to 0, right? So you're taking a ratio of two objects, both of which are very small. On the one hand, this volume is very small. On the other hand, this double integral of del f by del n times dA over the surface is also going to be small because the area is very small, right? So the ratio of these two things, the claim is, as the limit goes to 0, is basically nabla square f. And what this should remind you of is, it's a little bit like you know, in calculus, in basic calculus, in single variable calculus, the derivative is defined as the limit of a function plus some value minus the function divided by the value, right? So what you're dividing by, what you're normalizing by over here is the volume, and the numerator, so f of x plus h minus f of x, is somehow given by this double integral over here, right? Intuitively, this is like a limiting formula for the nabla square of f over here, but it's in the same spirit as how we tend to define derivatives in single variable calculus, okay? All right, so now let's look at the proof. There's a nice clean proof that William gave us. So he basically said that we have that this vector function f is the gradient of a scalar function small f. So now the triple integral T of nabla square f dv. So let's start with this triple integral here. So this triple integral of nabla square f, the Laplacian of f dv, is so the Laplacian of a scalar function is just the divergence of the corresponding vector function, but the vector function is just the divergence of f, right? Because the divergence of the gradient of f is the Laplacian of f. We've studied that before. This, by the divergence theorem, is f dot n dA. So we have f. So we have this equality over here. Now again, we can replace f as the gradient of this scalar function, and then write as del f by del n dA over here. Now the mean value theorem. So what does the mean value theorem for triple integrals tell us? So again, let's remind ourselves what the mean value theorem for single variable functions tells us. The mean value theorem tells us, well, if we have some region a to b, some boundary region a to b over here, and the function is well behaved, it's continuous and differentiable, then there must be some point in this region where the slope of the function, where df by dx is equal to fb minus fa by b minus a, right? That's how the mean value theorem behaves. So now if a and b are very close, then fb is going to be approximately equal to fa, right? So what the mean value theorem then tells us is that when the function is like when you take a very small interval, then df by dx times b minus a is approximately equal to fb minus fa, right? That's the mean value theorem, or you can view that as a first order approximation to the Taylor theorem, to the Taylor series expansion, right? So it's basically saying when you have a very small interval, the function is close to constant. So therefore you can just approximate the function. You can say that the derivative of the function is essentially constant in that interval, and then multiply that derivative by the length of that interval to get the rate of change of that function. You're approximating the function by a linear function over there. Okay, we'll see these issues in more detail in week 11, but right now we're just using engineering approximations. Okay, all right. So the same thing, the same mean value theorem holds for higher dimensions as well. So instead of a single variable, you can have a double variable, you can have a triple variable, you can have multiple variables, and the mean value theorem for these integrals is also going to hold over here. So that's basically what Vejia did. So he says that that when we are looking at this gradient of f, sorry. So when we are looking at so when we are looking at this divergence of f dv, when we are doing this integral, taking the triple integral, that's going to be if we take this volume to be very small, then we can treat this divergence of f like essentially a constant, and multiply by the volume of that object there, and that will be approximately equal to this quantity here. And then we use the calculus that we've already done over here to say that the divergence of f at that point is going to be 1 over that volume times this quantity over here that we've already derived. Okay, so then as the dt goes to 0, then you have the corresponding formula that you want. Okay, so the conceptual point to make over here is that when you have very small volumes, you can treat the rate of change of that function like the derivative of a single variable function, or the divergence of a function, the curl of a function. Each of these quantities is close to constant in a small volume when you have a very small region. Okay, so William is going to describe this.
就是上面的那一串东西，其实老师在他的 video 里面有一个叫做 application of divergence theorem 里面几乎是一模一样的，所以就是可以回去再看一下。然后下面那个就是用 triple integral 的积分中值定理的话，就是在那个算是那个体积里面那个 t 里面会存在一个点，使得关于这个点的这个 divergence 会等于再乘上这个整个的体积 v 会等于右边的那个积分项。然后当这个我们选的体积变得很小的时候，就相当于把那个里面存在一个点就赶到了一个很小的范围里面，就感觉像是以前学微分中值定理的时候，就是 fb 减 fa 除以那个 gb 减 ga， 然后 a 跟 b 很近的时候，那相当于就是洛必达法则成立的那个证明的那个思路。所以说最后体积变得很小的时候，就可以理解成它那一个点的 Laplacian 就等于右边的那个极限。
Zhejiang, you weren't paying attention? Okay. Well, let's say that the solution is good. Okay. So thank you. All right. Finally, okay, so let me remind you, so I messed up in the solution for part B, so that's still open. If anyone posts a solution by tomorrow, well, you get the bonus point, right? Otherwise, we'll post a solution by tomorrow, by the tutorial tomorrow. And remember that actually that's an important question, right? That would basically say that you only need to know the value, how the function behaves on the surface, and then you know how the function itself is behaving everywhere inside the region. Okay, so it's an important generalization of what we already know. Finally, question number 14. I wanted to request Marianne to come and help present question number 14. So okay, here we go. So question number 14. Over here, the calculations are not difficult, but it's useful to see again conditions where, like, why you have to worry about the conditions under which Stokes theorem, Green's theorem, divergence theorem, all of these apply or don't apply. And again, in your mind, you should be reminded of the calculations you did in week 9, where, like, for example, if a region was not simply connected, then you could not use the curl formula to compute the integral of a closed loop, right? Because there it's not applicable. Similarly, if a function is not continuous, then you cannot directly use Stokes' theorem to draw some conclusions, right? And over here, the question being asked is, okay, so evaluate the closed loop integral of f dot dr by ds times ds, where f is given by this minus yi plus xj over x square plus y square. The curve is the clockwise, the clockwise curve, the clockwise unit circle, x square plus y square equal to 1. Okay. Now, firstly, Stokes' theorem requires that, so let's look at the conditions. Stokes' theorem requires that, let's see, more general, okay, orientable small, yeah, okay, so I should have opened the classical Stokes' theorem. Let's see, the conditions for. Okay, so Stokes' theorem says, so suppose you have an oriented smooth surface bounded by a simple closed smooth boundary curve with positive orientation, and you have a vector function. You have a vector function f that is yeah. So simple closed smooth boundary curve with positive orientation. Okay, and let f be a vector field. I think you need continuity of that vector function everywhere in the bounding region, right? I should have. I'm sorry. I should have prepared this one a little bit better. So. Okay, so let me just do this by memory. So Stokes' theorem requires that when you're trying to convert this single integral of the curve to a double integral in the surface, like on that surface, the function should be well behaved. It should be continuous. Whereas this function over here, when x is equal to 0, when y is equal to 0, this function is going to be discontinuous over here, right? And that's going to give us a problem. So that's basically what Maya noted in his solution. So in question number 14, he did the integral. So firstly, just by doing the line integral, by doing the closed curve integral, by taking this function f, parametrizing it in polar coordinates, and integrating f dot dr by ds along this curve, and that gives you 2 pi. On the other hand, if you use Stokes' theorem, if you convert this to the curl of f, the curl of f cross the normal vector, and the normal vector is just a constant vector because the surface here is just the disk. So the curl of and the curl of f in this case, when you compute it, is also going to be pointing in that same direction. So in that case, you should just get the area enclosed by this curve over here, which is pi times r square, which is going to be equal to 1. So you skipped a couple of calculations here. They're not hard calculations, but if you can describe them in a little bit more detail for your classmates, that would be helpful. Okay, so the calculations that Mayan skipped over are that when you compute the curl of f cross the normal vector is pointing along the z direction. The curl of f is also pointing in the same direction. Then you get pi, and therefore these quantities are not the same, right? So we are basically out of time. So if you can just do a quick 1-minute summary of your solution, that would be great.
所以这道题其实就是按照它的要求把那个算出来，然后发现就它等式左右两边是不相同的，然后咱们就看一下那个 PPT 里面给出来的要用这个定理，然后它需要的要求是什么？其中有一条就是在这个它的定义域里边。这个方程它一定要是一个 continuous function， 所以如果检验一下 x y 等于0的那个点，就会发现它是不 continuous， 然后就可以直接 得出答案了，所以就比较简单。
Okay. All right. Thank you. All right. Yeah. Okay. So we're out of time today. Tomorrow we'll do one or two of the other questions we didn't have time to cover today. In particular, I apologize for the missing part B of question number 13. We'll try to revisit that if someone else hasn't already posted a solution. Separately, so tomorrow again we'll start discussing the projects again. Before tomorrow, before noon tomorrow, please upload your posters. So you had posters, right? You had posters for your projects. Please upload them to Piazza. Not Piazza, I'm sorry, to the Google Drive. So to the Google Drive folder, please upload your posters. Separately, I'd asked for people to shoot short videos describing their projects. So, just a 5-10 minute video just talking about your poster. It's pretty easy to record a video on Google Hangout. Let me show you how easy it is to record a video on Google Hangout. Indeed, that's what we're doing in today's class. That's what we do generally. So the way to record a video on Google Hangout is just go to just search for Google Hangout on air. Search for that. Click on this, and then click on live streaming events. New live event. Okay, and then you can fill in whatever you want to do. Go live now, and then you can do a screen share, and you can capture whatever is on the screen. So that's how we record class videos, right? And that's how you can also record your video talking about your poster. So please shoot a small video, a short video, 5 to 10 minute video describing your project. The reason we're asking you to do this is because not everyone had a chance to look at everyone else's poster, right? So for your classmates who may be interested in your project but may not have had a chance to see it yet, if you do this before tomorrow, then that will be helpful for them. Okay? So thank you. Class is over.